objective is to continue to learn about potential kinetic energy in the sense of learning about the law of conservation of energy. So your essential question is, how would I use the potential kinetic energy formula to demonstrate the law of conservation of energy? So we actually have talked about law of conservation before, but specifically law of conservation of mass. And what does the law of conservation of mass say? You're right. No mass can be destroyed or created, right? So what do you think the law of conservation of energy is?
Energy cannot be created or destroyed.
Energy cannot be created nor destroyed. It's the same law, it's just now pertaining to energy instead of mass. So, since energy cannot be created nor destroyed, basically what we realize and what we see is that energy then has to be transformed all the time. Okay, you can't create it, can't destroy it, but you can change it. So transforming energy is changing it. So we're going to see that energy transforms and goes through transformations all the time. Because we have a bunch of different types of energies. Now, when the energy is being transformed from one to another type, because of the law of conservation of energy, then even though it is changing, your total amount of energy must remain the same and cannot exceed what you started off with. So when you look at the law of conservation of energy, because it says that you can't destroy it or create it, but you can change it, as that change is occurring, your total energy will always be the same as what you started off with, and it cannot exceed or be more. So it can't be more, it can't be less. It has to be exactly the same. So if I start off with 100 joules of energy, I'm going to end up with 100 joules of energy. Now, is the energy that I end up with exactly the same type as what I started off with? No, but the same amount I will have. Okay? Now, most people say, but wait, I dropped that bouncy ball, or I dropped the tennis ball yesterday and it didn't come all the way up. And remember I said the reason for it is because energy got transformed into other things, right? One of the things is that every single time objects interact with other objects, there's friction. Well, friction causes energy to be transformed into the form of heat. So when you drop that bouncy ball down, when it hit the floor, that caused friction, causing heat. That heat dissipated to the environment. It also caused a sound. Sound dissipated out to the environment. So you, in quotation marks, lost energy. You didn't lose anything, but it just moved from your system to somewhere else. That is why the bouncy ball or the tennis ball didn't come back up to the exact same position, because some of that potential energy that you had in your hand when you let go got transformed or changed into heat and transformed and changed into sound, and it went out of your system. So it came back up, but didn't come back up to the same thing. And as it did it over and over again, more and more energy got transformed and taken away. And it's because of friction. Now, we know this, and that's what happens. But what we're going to do, when we do problems of law of conservation of energy, we are going to ignore friction. We're going to ignore friction. We're going to say that it doesn't happen. So we're going to ignore friction. Because if we ignore friction, it's easier to calculate because we know our total number and we know how it transfers equally. Okay? So, when we're looking at law of conservation of energy questions, I need you to ignore friction. So, nothing gets lost as heat, nothing gets lost as sound. Okay? It all stays in the system. Think that vacuum perfect world kind of thing. So, looking at this diagram, once again, I ignore friction. When I throw that ball up, and it's up here, I consider this point to have 100% potential energy and 0% kinetic. Now, once again, ignoring friction, ignoring everything, the molecular kinetic energy and so on. So I'm saying this has 100% potential energy and 0% kinetic energy. As it comes down, once it gets halfway to the floor, it has 50% potential energy, 50% kinetic energy. As it comes down, right before it hits, it's basically going the fastest speed that it's going to go. So it has 100% kinetic, 0% potential. Now, once again, these numbers are hypothetical, and we're ignoring a lot of different things. But the reason we're doing that is because when we look at these types of problems, we have to ignore them so these problems become easier. Now, when you get into more advanced physics, you won't be ignoring them. You're going to have to include friction and so on. But for our purposes, just so you understand how to use these formulas, we're going to ignore it. So since you do that, you are able to calculate amounts of energies knowing some specific things. So there's going to be two formulas you're going to have to know. Now, do you have to memorize these? No. You will get a formula chart. Now, are these going to be on the START test? No. This section of the notes, so this bottom section of the notes is only for IPC. So somehow mark from here down only IPC. The top you need to know for 8th grade STAR. The bottom you're knowing for IPC. Okay? Alright. When we do potential energy, the formula for potential energy is potential energy is equal to mass times gravity times the height. Guess what? You already did that in your lab. Didn't you do gravitational potential energy and did that calculation? You already used this formula. Okay, very easy formula. You multiply 3 numbers and it gives it to you, right? EP is potential energy. The unit will always be joules. M is your mass. Should always be in kilograms or newtons. So they give it to you in newtons. Height is always meters. Gravity is meters per second squared. Gravity is going to be a constant because it doesn't change unless you go to another planet. Gravity will always be 9.8 meters per second squared. So, and you don't have to memorize that number because it's also on the formula chart. But you will because you're going to use it a lot. Okay? For kinetic energy, it's 1/2 mass times velocity squared. So, think about it. Doesn't it make sense that you're going to include velocity if you're doing kinetic energy? Because what is kinetic energy? Moving. So you're going to include the speed. Kinetic energy, once again, is always in joules. Any energy is in joules. Mass will be in kilograms or newtons. Velocity, meters per second. So, looking at a couple problems. And actually, I messed up. We'll do doofus method on Thursday. I just want you to have it here. But remember, this part right here is only for IPC, not for STAR. Okay? So, any questions over the law of conservation of energy? Okay, so that's the end of the notes for today. You're going to add to those notes on Thursday. Okay?